So this course is called machine design, right? So given a problem, given if we have some requirements, we can design the shaft that can satisfy our needs. The functions of the shaft. You can see the shaft. So here on this shaft, I have a lot of other these components that are mounted on this shaft. So this shaft, you can see here also. This is my shaft. You can see I have a lot. This is other components. So what is function of shaft? First, the shaft is used to transfer the torque, right? So we have multiple shafts. They are parallel. So they are just to transfer the torque through gears. So if this shaft is rotating, driven by motor, I want to transfer the torque to this one. Then I can have two latching. This is the gears, and then I can transfer the torque. So second one is transfer bending loads and with minimum deflection. The bending loads. I will transfer the bending loads. The axial or thrust loads. Axial loads is in this structure. So this axial loads. So lastly, locate mounting of power transmitting machine elements, for example, gears, pulleys, belts, chains, the cams, flywheels, cranks, and rolling the element bearings. So we have a lot of things we're going to learn also. Gears we will learn, and flywheels we will learn, and so these rolling element bearings, and we will learn these elements as well. So for example, this is the gearbox and the function, and shows the function of this is shaft. Okay, so I have a shaft here. So this is my shaft number 1. So this is my shaft number 2. So these two shafts, they are connected by 2 gears. So this is my bigger gear. So this is my smaller gear. So these 2 gears, they are matching each other. So I can transfer this is the torque from either this one, this shaft, and to this shaft. So by the way, 30 years ago, a long time ago, when I took machine design class, I had a course designed for that, and we built this kind of gearbox. Okay? But at that time, 30 years ago, early 90s, we use the hands. But now you guys are using computer, right? You use computer to design, to draw everything. But at that time, we have a huge table, a huge ruler, and to draw this one using my hands. Pencils, different pencils. I'm old, I'm very old. That's 30 years ago. Okay, so design consideration. When we design the shaft, what do we need to consider? First one, the design shaft to be a statically determinate the structure. Can somebody tell me what is a statically determinate structure? What's your name? Okay, yeah.
Doesn't it have more variables than you can solve for in like a normal problem?
Say again?
More variables that are like definable in a problem in order to be able to be solved.
It's not exactly. Thank you, myself. Ready?
I would say it's that you have exactly the same amount of variables that you can solve. So everything is held in place firmly. It's rigid in place.
Yeah, very close. Okay. So this statically determinate means that I'm using these equations and we can solve the problems. The equations number and the variables number, unknown number are same. That's right? Statically determinate structure means that you can use the 3 force balance equations and the 3 moment balance equations and to solve the problem. You do not need to do anything, need any more information. Okay? One more time. And you can use the 6 balance equations, 3 force balance equations, and 3 moment balance equations to solve the problem. You do not need to know to have any additional information. So what is this is on opposite. So this is statically indeterminate structure means that you need to have more information because you have more unknowns than the equations you have. That's called statically undeterminate the structure. So this is know that. Second one, avoid cantilever beams. The cantilever beam is bad. Why? Because cantilever beam is that for this beam or shaft, only one end is fixed, and the other end is not fixed. Then the deflection might be very, very huge. So this cantilever beam. Avoid the stress concentrations. And stress concentrations, they are bad. Okay, so why bad? Because in the neighborhood, and so this stress can be very, very local stress can be very, very huge. And keep shafts as short as possible and with bearings close to the applied loads. So this is reduces deflections and bearing loads and increase critical speed. So because the shaft is rotating, and rotating means what? Rotating means of frequency, right? How fast it rotates. And this is very, very unique. And we are going to do the natural frequency analysis. And we are going to use abacus again. I'm sorry, guys. And because when you design a shaft, you know the operating conditions, right? So usually, what is the frequency of this is the shaft rotating, and then you need to know that this natural frequency of the natural frequency is related to the geometry, the material, right? So you need to do the natural frequency analysis to make sure your operating frequency of the shaft is far away from the natural frequency. Otherwise, resonance can cause a big trouble. You know resonance, right? Good. So one weight is critical and consider hollow shafts. The hollow shaft is if the weight is very critical, you can just use a hollow shaft instead of use a solid. Any questions regarding this slide? For this slide, I want you to know what is the statically determinate structure. So number of bearings on the shaft now here. So here, look at I just give you an example. 3 bearings for here, and we have 1 shaft for this case, and we have 3 bearings, and the 3 bearings over constrain the shaft and introduce preload on the bearing also, and they are more difficult to assemble. 3. So these are statically indeterminate the structure. Why? Because you have this is the load, and so this is a reaction, and you have more the unknowns to solve than the equations you have. So this is over constraint. Over constraint, ideally, okay, if both the shaft and these 3 bearings, they are ideally created, ideally manufactured, that's okay. But you already know this is not the case. Manufacturing, most of you guys are taking manufacturing, right? Manufacturing, we have some dimensional accuracy, dimensional this deviation. If this is the case, this will be a problem. So here, this one will be much better. So 3 bearings determine the location of shaft accurately. Also, it is statically determined the structure. And so we have only 2 reactions. Reaction 1, reaction 2, and so number of unknowns equals the number of the equations available. So we can solve this problem very, very beautifully, right? Without any other additional information. Questions regarding this slide? No question? No question. So also, when you assemble, this is the shaft, this is our shaft, and we have this one component, that one component, and we need to allow this thermal expansion. And because when usually when this is the shaft is rotating, it generates the heat. The heat and this expansion, all these components are connected to this shaft and will be expanded. So when this expands, and you need to take care of this expansion. Left bearing, okay, so this is left bearing, and takes the axial load. So this is, you can see that the step, and so this can take the axial load because there is no clearance. And the red barons are those for the thermal expansion. You can see here, okay? I have some expansions, I have some clearance and to allow it to expand. So in this system, accurate load calculations are possible. Questions regarding this one? So this is one baryon, so this is one baryon. So this baryon does not have clearance, so as a result, this guy can carry the actual load. But here, we want, we allow for this is thermal expansion, so we have some clearance here. So this is our shot.
In that case, what would be expanding? Would it be the bearing? Or-
This one will be bearing. This one will be expanding. That's a good question. So the maximum deformations in design bearing. So this one, which one is good for this one? That's that one, right? Because you can see the pressure distribution is kind of uniform, but this over here is a very huge spike, and this is almost zero. Right? That one is good, right? Good. A sudden change in stiffness. So the second one, this one is better. So two keys on a shout. So you know keys, right? I'm not talking about the keys, my door. I'm talking about this kind of key. This key means that, so you can see, so if I have a shout, and I want to mount some gears or other components on it, and in turn, how can I make sure when this is the shaft rotates, so this is mounted components will be rotating together? How can I make sure? I use keys, right? These are keys. This is called keys. We try to transmit the torque. We need to constrain the gear's rotation with respect to the shaft, and it requires one constraint. Therefore, one key is required. You can see. So this is my shaft. So this is my gear. If the shaft is rotating, I want to transfer the. I want to let this torque rotate also. So there must have a key. This key will transfer the torque from the shaft to the gear. The second key over constrain the gear and creates undesirable stress. So theoretically, one key will be good enough. If you have two keys, this is one key. If you have two keys, guys,